Welcome. In this module, we are going to discuss about what is known as spinodal decomposition. So, I am going to follow Hilliard's article and I am going to tell you about some historical information as to how this understanding of spinodal came about, or what are the important steps towards the development of an understanding of spinodal decomposition. Reportedly, the first observation of this or reported observation of spinodal was by Bradley. He was looking at copper nickel iron alloys. These were quenched and annealed inside the miscibility gap. When he did that, he is reportedly had seen in X-ray diffraction pattern side bands or satellite spots around the Bragg peaks. So, he took copper nickel iron alloy, he quenched it and annealed it inside the miscibility gap, and when he did X-ray diffraction, he saw extra spots or streaking of the existing spots in addition to the regular Bragg peaks that you would see. So, this is reported because this is not Bradley's paper, but in a paper which was written. So, this happened in early 1940s. In 1943-44, Daniel and Lipson were the ones who took this copper nickel iron alloy and did a lot more of studies, and they report that Bradley had actually reported this. And what they did is that they tried to explain these side bands. They showed that the side bands correspond to periodic composition modulations. If there are periodic composition modulations, then such side bands or satellite spots are expected. So, that is the first thing. And the second thing is that they showed that this happens composition modulation from the experiments, that these composition modulations are along the 100 directions of or crystallographic directions of the sample. And in addition, they also calculated the wavelength and they showed that it is of the order of 100 angstroms. Okay, so, Bradley has reported satellite spots or streaking of Bragg spots, and Daniel and Lipson explained that such spots can arise because of compositional modulations, and specifically in copper nickel iron they said that these composition modulations are along the 100 direction, and the wavelength of the composition modulation that they calculated from their experiments was about 100 angstroms. Now, growth of composition modulation in an initially homogeneous alloy implies uphill diffusion. So, this we have seen the classical diffusion equation, Fick's law, in addition to if you combine it with the law of conservation of mass, the so called Fick's second law, is a statement of the fact that if there are compositional heterogeneities, they will be evened out. So, if you are starting with an alloy which does not have compositional heterogeneities, and if it develops compositional heterogeneities, that means the diffusion is taking place from regions which are poorer in some composition to regions which are richer in some composition. Now, that means uphill diffusion, and by Fick's first law, uphill diffusion means negative diffusion coefficient. So, basically Lipson, Daniel and Lipson's experiment showed that there are regions which behave as if the diffusion coefficient is negative. So, the uphill diffusion is what they have reported. Independently, much earlier in sometime in 1937, Becker and Dehlinger, both of them, but independently, have shown that any time you have this kind of spinodal region or phase separating region, we will exactly define what spinodal is. For now, it is a region in which some regions which are rich in A become richer in A, and some regions which are poorer in B become poorer in B. So, whenever there are such spinodal regions, it is expected that the diffusivity will be negative. So, this was independently sort of postulated by Becker and Dehlinger sometime in 1937. So, the experiments of Daniel and Lipson are in 1943-44, and they sort of agreed with Becker and Dehlinger's prediction that inside the spinodal region you will find diffusivities to be negative. But what the Becker and Dehlinger kind of theories cannot explain, in fact any theory which is based on Fick's laws, the classical Fick's laws cannot explain, is the fact that there is an wavelength of the order of 100 angstroms. Okay, so we will show as part of this course at some point that if you use classical Fick's laws, then it leads to contradictions in terms of its predictions. Okay, so there was a problem. So it was known that you will have this negative diffusion coefficient regions or uphill diffusion in some systems which undergo this kind of phase separation. And but what was more that was given by Daniel and Lipson is the wavelength of a modulation which was not predicted, which was it was very difficult to understand why such wavelength exists. So in fact, we can show that any model which is based on Fick's law will give you wrong results, so contradictory results. Then Max Hillert, in his PhD thesis written sometime in 1956 and a paper which followed sometime in 1961, had done atomistic model. Okay, so he took a regular solution model, and so his model was based on the regular solution model, and he took discrete lattice, and on that he tried to solve the 1D diffusion equation. So he set up a flux equation for 1D diffusion on the discrete lattice, and he solved this problem numerically, and using a regular solution model, using a discrete lattice, setting up 1D diffusion equation for the flux of atoms, and taking such equations and solving them numerically, Hillert obtained the solution, namely that periodic variation of composition with the position is expected in such systems. Okay. So it is a regular solution model, it is on discrete lattice, and it is a flux law that was proposed, but that is slightly different from Fick's law, in which way we will see later. And using that, he showed that it is possible to get solutions of this type, where the composition modulates with position. And he also did some calculations to show that these compositional fluctuations are expected to be of the order of 100 angstroms, which was seen in copper nickel iron by Daniel and Lipson. So this was one of the important improvements in the understanding of spinodal decomposition. So this is one of the important studies that happened. And Kahn in 1961-62 came up with a more flexible continuum version, which basically incorporated the same physics as was suggested by the model of Hillert. Okay, so we are going to look in greater detail as to what this modification that was suggested by Hillert is, and how it was incorporated in the continuum models by Kahn, which led to eventually the so called Kahn-Hilliard equation for studying spinodal decomposition. Okay, so this is the sort of historical timeline. So 37 or so, people knew that diffusivities can become negative inside the spinodal regime, but experimentally that there is something strange going on was first reported by Bradley. Then Daniel and Lipson did in copper nickel iron alloys lots of detailed studies, which showed that there are composition modulations, specifically along the 100 directions in these alloys, and the composition modulations have a wavelength of about 100 angstroms. But the Becker and Dehlinger kind of theories will not explain such composition modulation, even though they do explain uphill diffusion and negative diffusion coefficient, or they at least postulate that there will be negative diffusion coefficient regions. So it is seen that there are such regions, so experimental evidence is available, but what is not clear is why a particular wavelength is chosen. And later Hillert, with his regular solution model and discrete lattice based theories, he postulated the problem of flux of atoms in 1D on such discrete lattice or in systems which obey regular solution model. He did some modifications, which we will discuss in greater detail later. So he showed that it is possible to get the solution of composition modulations or compositions which change with position as a solution for such problems, and he sort of indicated that the 100 angstrom wavelength that has been seen in experiments is expected in under certain circumstances. So, it is a very simple model, it is a discrete lattice model, and later it was developed into a continuum model by Kahn in 1961-62, resulting in the so called Kahn-Hilliard model, which is the modified diffusion equation or non-classical diffusion equation. So, we are going to look at these things in greater detail. So, what Kahn did along with his co-workers, and how it explains what is happening in phase separating systems is something that we are going to do in greater detail. So, in the next couple of modules, we will discuss about spinodal in greater detail. What is spinodal and why does it happen, what is its physical significance, and things like that is what we will discuss in the next couple of modules. Thank you.